So, welcome all. I hope you can hear me. Let's start today's session. We are into our eighth week of a live interaction series on the course of Applied Numerical Methods, NPTEL 25 course, ME97, offered by Professor Malay Kumar Das. I'm the teaching assistant Shrey Sahai Gupta. I'm a doctoral student at IIC Bangalore. Um, I'm in my fifth year of PhD. Uh, Please note my email ID. If required, you can always reach me out. Um, and yeah, this was a page just to say hi. Um, Most of you by now would already know me. So let's get started quickly by just reviewing what have we been doing in the last few classes. Well, in the last class, our discussion towards numerical linear algebra was something that I had started with, but in that course, we had a series of questions from the students. Basically, one topic which someone wanted me to quickly look at was shooting methods. So that is something that I would do. Because shooting methods is more or less explore or like it's there in the books, at least the numerical part of it. I wanted to quickly give a background in it, and turned out that it was Plossius equation um, that was being uh, that was the equation of in question when shooting methods are generally explored, and that was the case even in this course. So I before I would have started with uh, the algorithm itself, I just wanted to quickly give a brief overview of how this equation comes in, and without deriving too much derivations and stuff, just wanted to quickly give a feeler of this problem, the background, the backdrop of this problem. And while we were at it, someone because it required some of the so now finally we were in this position of we had written all that feeler was done. We were in the position of solving this equation, and while we were at it, someone asked a follow-up question on what are eigenvalues. So that was something that we had a small discussion on. Especially eigenvalues are used in different contexts, and there are eigenvalue problems, there are eigenvalues of a system, and so on. So in different contexts, we use eigenvalues, but essentially they arise from like eigenvalues find their definition from existence of a matrix, be it a one dimensional one cross one dimensional matrix, be it that small, but eigenvalues um, have to come from a matrix. That is something which I tried to stress upon. So, so that is where we had stopped because it was 2 hours. That is what is the stipulated time of our sessions have to be. Uh, Anyways, before I continue on this discussion, let's also quickly look at what we were doing in last in the last to last and second last to last class. So now or maybe we can look at it from the entire 7 lectures that we have ex like we have attended or we have done. So the first lecture was what the glimpse of numerical methods. Then I guess the first four, right? So first 4 weeks of them were on applied uh, finite difference methods, not finite difference, finite approximation methods. Maybe the fifth one as well was on it, but what was the sixth one? Let me quickly remember this stuff. Mm, Yeah, there was also a discussion that we had on a big O notation. That was not a big discussion. Anyways, so yeah, I guess yeah, I don't exactly remember what we had been doing in the second last session. Ah, so there was one session where we just coded out our the sixth session was more or less the coding part of finite element method, I guess. This is where we had stopped, and yeah, that's it. This is where we had stopped. There was some discussion on TDMA and how TDMA can be without requiring to do any decomposition, LU decomposition, or for that matter, it didn't need. We just can do it using an algorithm. We don't need explicit storage of values into a matrix with TDMA, especially if your matrix is tridiagonal. So now let's continue with our shooting method before getting into numerical algebra stuff, where we are basically trying to explore singular value decomposition. That is something that I want to look at. Just give me one more second to see if there is something on the script that I had prepared. So these are this is the document where I note down things to discuss. Yeah, yes. So some bits and pieces I had tried to look into it, but let's see. Okay, so this is something that we have to do anyways. So let's look at uh trying to solve a Gaussian equation, and let's continue. So we were somewhere here, and now you see that this equation is not a linear set of equations. This system of equations are not linear in the sense that you find a non-linearity going on here. Suppose there was no non-linearity, then we could have written this equation as in this format. And let me write if linear, if it was linear, then we could have done something with matrices, and then an eigenvalue kind of concept could have come in, and how it would have looked like. Suppose this was just this, right? So then you can actually write A, where your A would be this. Let me write. mm, This is there. Yeah. So let's look at it. So F dash is equals to 0 into F, 1 into G, and 0 into H. Then G dash is equals to 0 into F, 0 into G, and 1 into H. And H dash would be 0 or H dot 0 and minus 1 by 2. So this could be something if this was a linear system, but we have F into Fg. Suppose it was just F by 2. So then this minus 1 by 2 would have changed its position to somewhere here. Now we can't write this as a linear set system of equations because we have a non-linearity associated with it. No matter what, we can still use uh, any integration scheme, be it Runge or anything, and then use this uh, to solve our system of equations. Now, before I get into why or just go ahead and solving this equation, the problem we have here at hand is that we don't have this sort of boundary condition. It's only an initial value problem that Runga can solve. So what is an initial value problem versus a boundary value problem? So initial value problem states is a problem where all your boundary conditions are specified at the same boundary. If all your conditions are at the same boundary, then you essentially what you have is a initial value problem. because you can now iterate in the direction opposite, in the direction away from your um, one boundary, and then you will, what you will have is um, so you can evolve away from this boundary to get the solution. That's the logic of initial value problem, especially in transient calculations, in transient conditions or transient systems. uh, you know a lot of things at only t equals to 0, and that is why a lot of initial value problems come in form of transient for problems, right? Now, in our case, we are, if you would note that what we are solving is a uh, uh, steady 1D problem per se, especially we are looking into the uh, the velocity profile in the direction of in the transverse direction away from the wall. So it's a 1D problem, and this 1D problem does not have a boundary condition at uh, all at one end. Instead, we have this kind of situation. We have three conditions, and that three conditions should suffice with the three degrees of three order third order differential equation. So we need three conditions, exactly three conditions to find a unique solution. But the problem is that at infinite we don't have the third condition at zero, so we can't evolve as Runga or say any other initial value problem. So any scheme that allows you to solve a initial value problem, we can't actually extend it, and that is where shooting methods come in. You can actually use a shooting method to solve boundary value problems. That is one way. Uh, Also, a shooting method is makes sense only in certain criteria. It won't make sense if you try to solve a uh, suppose a 2D kind of problem where you have a square, let's say a rectangular domain, and you know two boundary conditions at so suppose suppose it's a two-dimensional, yeah, as I said, as a rectangular domain, and now you suppose you have temperature boundary conditions at all four boundaries. So there, shooting method won't make a lot of sense because it will have a lot of unknowns there that you would have to um, iterate over. And that essentially means that in some sense you're using more of hit and trial and less of common or numerical technique to solve the field. So there are other better ways to do it, uh, but in a case of 1D kind of situation where you know there is only one boundary condition that you have to iterate over, shooting methods make more sense. Even in certain cases, we can shoot over two variables, but it has to stop somewhere because it becomes more and more numerically tedious to keep guessing as number of unknowns increases. So suppose in a rectangular domain, if you start shooting, you pick one boundary and you start shooting for all other three um, yeah, all other three boundary conditions at these say at this boundary and try to guess the so what you do is in a shooting method what you do is uh, so let us also quickly understand what shooting method is. So before I could actually explain why shooting method would not make sense in a multi-dimensional setting is that so in shooting method you guess uh, a boundary condition, a condition to pose a boundary value problem as the initial value problem and use root finding algorithms to iterate over the iterate over the gas condition such that the left boundary condition is met. So let me, maybe this is not clear enough. So what essentially are we talking about? Let's look at it. And just before I do that, maybe also I'll explore what Wikipedia says about about shooting method. So that, yeah. So it says in numerical analysis, the shooting method is a method for solving a boundary value problem by reducing it to an initial value problem. So that makes sense. It involves finding solutions to an initial value problem for different initial conditions until one finds the solution that also satisfies the boundary condition for the boundary value problem. In layman terms, one shoots out trajectories uh, in different directions from one boundary until one finds the trajectory that hits the other boundary condition. So what essentially do are we saying? Yeah, one last. So as I mentioned, see, there is an so you have to use standard route finding algorithms at one point of time. That is there. There are linear shooting methods, which I think this is Newton-Raphson, I guess. And what else? Okay, so it says eigenvalue problem. Let's look at what this is. The shooting method can also be used to solve eigenvalue problems. Consider this kind of a situation. The problem can be solved analytically to find the energies, but also serve as excellent illustrations of the shooting method. Uh, okay, okay. Yeah. So wait. One thing is, what do I mean? Suppose I have two boundaries, and what I know is f value of I know f value at 0. Suppose this is what I know. I know f of 0, and then I would know f of 1. But now to solve it using a initial value problem algo, I also need f dash of 0, right? And this is something that I will have to guess. If I actually need to reduce this problem to a initial value problem. So this is something that I will have to guess. And so what essentially, this is something that we will have to guess. So suppose I guess it, and with that guessing, I try to integrate over it and try to find what f is, right? Uh, so now, suppose you traject like this, suppose with this guess, and because you have a boundary condition and you have a differential equation, you traverse like this, whereas your f1 is something somewhere here. So now you repeat your guess based on this error. You guess a different value. So then hi Apurva, just give me a second.
Yes, good evening.
Good evening. Yes. So I was actually recording the stuff which you asked about in the last session. It was you, right? About the shooting methods, right?
Yes,
Great. So just give me a second. Um, let's do this. So, so what I was discussing just before you joined, see, we discussed parts of the problem that we need to solve or actually pose the problem as a system of first order equations before we can actually use our traditional initial value problems, right? It turns out that any order of equation can be posed as a set system of linear equations if you break them down in this sort of manner, right? This is something that you are familiar with because you've seen this in your lecture notes also. But now, what shooting method is all about is that you guess the required number of conditions at one boundary, and you evolve over it using your initial value problem as an initial value problem, and you see if you can actually somehow reach the post boundary condition. So suppose you know f0 and f dash of 0 is also known, but you know you so f dash of 0 is not known. Sorry, f dash of 0 is not known. F of 0 is known and f of 1 is known. So what you do in a shooting method is you guess f dash of 0 and start evolving it as a let's say RK4, and what you end up with is a different f1 of value. So f1 of value f1, but not exactly f1 but f1 star. So what you do is you correct your guess based on this error so that you can somehow approach this f of 1 value. Okay, so just give me a second before. Just give me a second. I might. Yeah. So yes. So now if you evolve over it, maybe some other trajectory will come and you will reach closer to f1 of value f to the prescribed boundary condition at the other end, and eventually you would have to use root finding algorithms to correct your guess. Just like how we knew that if we so there were root finding algorithms, right? In the initial we looked at it, and using that root finding algo, you keep on traversing over this f dash of 0 to find the correct f dash of 0 to reach f of 1. That is the logic there. Actually, this might also help you if you look into this problem. So just look at how Wikipedia explains it. That shooting method reduces the boundary value problem to an initial value problem and find solution to the IVP for different initial conditions. So basically, we are traversing over the unknown initial condition, different initial conditions until we find the solution that also satisfies the boundary condition of the boundary value problem. So maybe you can look at this as well. This clearly describes what a shooting method is all about. And now let's look at its implementation also. Um, yeah, great. At this, or I didn't ask you if you have some questions already or anything. Maybe we can explore that just after we finish this shooting method. So yeah, and the last time I also kind of opened a book, right? You remember? You would remember I opened a book and there was some problem. So yeah, it's there. And this is the same problem, and I actually would like to look into this, like approach this shooting method using this like this problem as well. So but I don't want to get into it too much. Let's start solving the Bloch's equation and see how it does it go. Okay, so let me start my console that we can start coding this.
So for Brazier's problem, we will get three first order equations, right? I mean, the governing equation is of third order. So by using shooting method, we'll get three first order equations, right?
Right, but it's not the shooting method which is giving you the
Yes,
three first
yes,
order equations.
that is not correct. Yes.
Yeah, just yeah, this is a what do I say? This is the magic of I don't know
And
maths
transform
maybe. Yeah,
transformation.
yes, kind of transformation only. Basically, you're changing the representation of the system. That's it. Yeah, nothing big there. Yes, but it's nice. We don't it's not apparent at the first go that this is possible, right? Any higher order equation gets becomes a, what do you say, system of first order equation is something that you won't expect. So it is an important thing. It does, and maybe there is a name to it also, but I'm not sure. So let's start coding this. Um, so today is 16th, right? Let me open this up. Yeah. So this is shooting method 16th September. So just like every time, I'm gonna import two important libraries. One is to handle arrays, and one is for plotting and stuff. Import matplot lib.py plot. Just remind me to also discuss once this ends. Let me also remind us, because I found something on eigenvalue problems. Maybe that will close the discussion we were having last time also. Maybe this is something that I'll look into towards the once I finish with the shooting method. So SPLT, and then we'll also import another library called as solve IVP. Maybe you can also use it, but if you are familiar with Rungakutta, let's also look at how Rungakutta RK4, right? Rungakutta. So it is important to note this fact that Rungakutta is in sort of is a, what do you say, is posed as a first order equation problem. That is an important thing. It's a first order initial value problem solver. It's not a like general solver. So we have to pose every problem as a first order initial value problem. That is why we need to transform this set of this Bloch's equation into three first order equations and so on. So we can actually use this scheme, but I'm not gonna implement it myself, but I'm gonna use a different library for this. So that library is from the SciPy uh, package, scipy.integrate import solve IVP, right? And let's use that. Now, okay. So now if we have to code this out, how do we do it? Um, so the way solve IP works is that you need to give it. So basically, so let's forget about shooting one for us for a ta- for once, and let's look at how we will integrate it once if this was an initial value problem. Suppose we knew that f double dash of 0 is, let's say, 2, or anything else for that matter. Let's take something else. Let's take pi. Now, the important thing is in shooting method, we have to first fix which boundary condition are we going to traverse at. And the most logical boundary condition is the lowest derivative, right? We could have traversed over third order derivative also, but that won't make sense. If we knew functional value, we know the first derivative. So it only makes sense to second guess. So it only makes sense to guess the second derivative, right? So let's do that. This could also be a difficult choice when trying to shoot, right? You have to be you should know what like which variable are you trying to estimate in order to find f dash of infinity, right? So now you understand that point of view, right? Or it's just confusing.
Yes, can you repeat once?
So basically what I was trying to imply there was see this so uh, let me pose this entire thing more formally. Okay, so now what do we have here is this should be put more carefully. So now we are here, right? We are here. This is the thing. And let me change this F to some capital F. So that, right? So now what are we trying to write? We are trying to write as df by dt is some function, some function. What do I put? So what do I write here, Apur? Let's let's write this capital F. Let's write this f of f and f. Now what is this? What is this? This is a, first of all, this has to be a matrix and this has to be a vector. Okay, this is also a vector. And sorry, so this is a matrix and this is a vector. Okay, so for us, it is important to first write this also down, that this is F, then G, and then H, right? And then what is capital F? It is G, H, and minus F by FH by 2, right? Think now it is clear to you, right? So essentially, in our case, F is not a function of T anymore. It's just a function of F, right? Uh, Now, what I was trying to imply is that we know, what do we know? What boundary conditions are we aware of? So we know f of 0 is 0, and we also know f dash of 0 is also 0, right? Yes, but we are not aware of, and one last thing is f dash of infinity, or let me write f dash of eta much greater than 1, which is essentially infinity, is 1. Now, my question to you is, when you try to solve this system of equation using Runga-Kutta, what kind of boundary conditions do you have? Do you have f of 0? Actually, this makes it more precise. I was kind of saying something wrong. So we know f of 0 is 0 and g of 0 is 0. So this is also g, right? This is g of 0. So this writing it this way makes it clear what boundary condition we need to assume. See, we need to assume h, right? We need h of 0 to start solving, posing this as an initial value problem, right? Does that make sense? We need f of 0, right?
Yes, sir.
So this has to be 0, 0, and something, right? But my only submission is that sometimes we could have guessed f triple dash also. We could have guessed h dash also, or something of that sort. Why? And because we have this initial equation, right? See, in this case, it will make more sense guessing f double dash or h. So if I were to write this, this is h now, and this is h dash, isn't it? So we could have guessed, we could equivalently guess either h or h dash, because we have f, so we can either guess h or h dash. This is just the same thing. But sometimes it would require you to uh, choose which value to guess. For example, in our initial value format, it is now clear that we essentially need h. So just simply guess h only. Don't guess anything else. So that is what I was trying to say. Maybe I complicated it a little bit, but anyways, this is the whole business there. So we will guess h of 0, which is what? Which is f double dash of 0. Okay. Um, Fine. Um, yes. So now let me write, first of all, let me write df definition df dt. So that will make sense to you. And the way you have to define this is like this. So you have to define t and then f. Now you write f comma g comma h is f of 0, f of 1, and f of 2. Okay, the why am I able to write this function? How do I know I have to write this function is something I know how solve IVP works. Or at some point we actually need this kind of format, right? We need this. You understand this, right? I'll show you how this is. So writing this equation is in numeric or in the for the computer to know. I am writing this function. I'll tell you how, and then you return um, this. So you return. So what is df by dt? It's g h and then minus f into h by 2, isn't it? Let us check once. G h minus f into h by 2. So this will be our this kind of equation. This thing. This essentially this is the equation we are trying to solve, right? That makes sense, right? And solve IVP needs exactly this kind of stuff. So first, let me show you what solve IVP does. So suppose you have some function definition dy by dt, and dy by dt is let's say t comma y, and you write return minus 1 into y or minus y. Okay. So now if I use this and I solve using solve IVP, what essentially it does is you have to first define what is your dy by dt term, what is your initial value. So initial value has to be given, let's say it is 1. Then you also have to specify the time over which you are trying, or the uh, integration domain or range where you want to integrate it over. So t, then you have to actually write this t span is equals to this. So let's say 0 to 10. And then a method we can also specify. So let's specify RK45. Okay, now this is a little complicated. So let me help this with this also. Tspan solve. Solve IAP. So when in Python, you can use this function to figure out how does your like what are your inputs, what are your parameters, what kind of output it gives. But and you can read through it. Essentially, these are important parameters that you need to run solve IAP. So the function that gives you dy by dt, the initial value, the span over which you want to integrate, and a method. You have a list of methods. There are implicit methods, there are explicit methods. You can go through it. Maybe I'll spend some time over on it also. It's an interesting, important observation. Um, so maybe you can look at that also. So methods are also important. Maybe we can look at that also. So now just let me show you how this solution looks like. So let me plot plt.plot solution dot t and then solution dot y dot think solution dot solution, I guess. No, solution dot y. What is it? So wait. So solution dot t is fine, right? Yeah, and then solution dot this is something that you would have to know. If you unless you know this thing, you can't use solution dot y. So you have to know that once you run solve IVP, then the output it gives has two parameters t and y, and that this is where your data is stored and something like that. So only then you can do this. Now, yeah, and then you will have to do this. Yeah, see, this is how it looks like. And then there is also another um, as maximum step. So that could be given as 0.1, and then you'll get a smoother curve. PLT dot plot. So great. Suppose this is clear, right? Is there a confusion with this implementation? First of all, let me give something else. Let me give 1. Why? So you know now the eigenvalue is a positive eigenvalue, so this will shoot up. See, it shoots up to a very high value. Let me give it a small value, minus 0.1, like this. Let me give 0.999. Yeah. So this is how it would look. This is the simple equation of dy by dt plus y equals to 0. This is what it is, right? This is the simple equation. This is what I have tried to solve with the initial implementation of it. This stuff is clear, right? Let me know if it
Yes,
is
sir.
not. Minus y. Okay. So similarly, now we can actually use solve IVP to use df by dt also. Okay. What do you write? Intro to solve IVP. Okay. Now let's write. Let me write. Let me use. Now let's look at how df by dt would look like. Okay. So if we were to integrate it as suppose we knew the initial condition, then how this would look like. So just let me solve IVP for lossless system. Okay, so now simple stuff, nothing great there. You will have to just give the initial condition there, right? So now you will have to give some initial condition, say alpha, where alpha is something that we will define. Okay. Let's say alpha is 0.1. Okay. There are three. Uh, so first of all, let's note what is going on. So I don't like this sonority. Give me a second. Okay. I cannot go down only. What is this? Hmm. So as I was saying, you will get actually three functions that there will be three functions, F, G, and H, right? So you will get three functions. There will be three plots. Now in this case, you see that the first and the second plots are kind of overlapping. If you note this, right? Um, label And this is G and this is H. That's PLT dot legend. The blue line is for F, G is for orange, and H is for the green one. Um, Something is off. Let me check. Yeah, the off thing is here. Should be df by dt. See, yeah, something of this sort is what you will get. Let's look at only. Let's decrease the span to 2. Or 10 maybe. Okay. Now, Arun, Apurv, I need a little bit of discussion with you. You see how this thing you found that, so you can see that we are kind of we are able to evolve over, what do you say, we're able to evolve over this Plossius system, right? We are able to integrate it once I know the initial condition of H. Let me say H0 rather than say alpha. Let me say H0 and then G0 and F0. Okay, F0, G0 and H0. 0, comma 0, comma zero, 0.1, let's say. Here I will put alpha. And we have a small discussion if you're there.
Yes, sir.
Okay, so you can see that that there is an evolution there. Now tell me what is the boundary condition that is left for us that we didn't impose, that we didn't impose, right? We didn't impose, right? There is a boundary condition we didn't impose, which is what? G of infinity is 1, right? This f dash is G, right?
Yes, sir.
So this is G of 1. Now let's note one important thing about this solution. You see how G is kind of asymptotically going to a constant value. Let's increase the domain to C. See, G is kind of constant after some point of time.
But it is not tending to one. That is a problem.
That is the problem. You get it. But the important thing is that it is a constant, right?
And
And
physically, it is
so
also, yes, sir. It is going constant, but just the value is not correct.
yeah, that is where the shooting will come in. Now, um, we'll first let's rather than implementing like numerically doing shooting, let's try to do shooting ourselves. So let's hit and try and see if we can approach one. Okay, and that is essentially what route finding will also do. A route finding algorithm will do, and that's it. We are done with shooting method. A route finding algorithm, if we apply, see, if we iterate over alpha, and the error is this G of 20. So first of all, before I go there, just first let's realize that G of infinity can be imposed rather than imposing G of like we can impose 1 at 20 only, right? Or 10 for that matter. Does that make sense? Can we just look at in the domain of 0 to 10 rather than going from 0 to infinity?
Yes, sir, because it is already going like flat from 5
Yes.
onwards.
Yeah, that is one thing that I wanted just for you to note. Now, as I was saying, let's iterate. Guess a different value. So give me a different value. Alpha for alpha that I can look at.
I think point 2, point 3, whatever.
Yeah. So let's say 0.2. And what do we note? So let me also print what the G value is finally. So sol dot y 1 minus 1. So initially it was for the case of 0.1, it was 0.44. We need 1. So then now we traverse over 0.2, and now we are closer to 1. So we know that we are kind of getting close. Now you said 0.3, 0.93, good. Let's try with 0.4. Ah, see, the value has gone above 1. So somewhere 0.3, 0.4, we have to be there. Okay. So now let's write a function which can figure out this root. Either we can do it R manually also, 35. Let's say we are close to this thing, but it's higher than 1. So we know it's somewhere between 35 and 30. So let's go to 32. So we are a little below 1. So somewhere higher. So let's say 33. Oh, just a little bit like that. I know that the final value is going to be this 332. This is where it kind of approaches. We can, if I play this, yeah, see 1 point exactly. So I knew that alpha is 0.332. So, but anyways, suppose we don't know that. Suppose that is something not known to us. So now in that case, what do you do is you write a root finding algorithm, and that root finding algorithm. Okay, before I do that, let me also introduce root finding. Introduce root finding.
Actually, the confusion arose because I didn't think of root finding in this. Now I can get like I have an insight in the problem.
So essentially you have to implement root finding. The whole issue was about root finding, I guess. So that once you include root finding there, that you're done. You're done. That's it. If you want me to continue, we can do it. Otherwise, it's done. The problem is done. See, we can close. We knew that it's 332. We could have done it manually only, right? The exact value kind of comes close to this value, and it's around 1. Okay. And yeah, this is your Blossius solution. This is the velocity profile. So if I were to just plot the velocity profile for us, quickly I'll plot the velocity profile. One important thing to note there also is it's actually important there that this is not the velocity profile per se. This is just G. So that is also important, but maybe see, this is how the velocity profile looks like. Okay, so at a wall it is 0, but away from the wall it will be that far stream velocity. Um, and this I should put it as Pleiadian vector ratio something 1, something like that. PLT dot. Just give me a second. PLT dot set aspect I equal. Okay, okay. Yeah. Now, one more thing, one last thing is, um, yeah, so I think we don't need to go through the root finding part of it. This is the velocity. One thing is that this is not velocity profile. You have to first multiply. So this is G, this is F dash of eta. So first of all, you have to, this is not Y, or this is not the transverse direct, this is not distance Y. This is actually distance normalized by the boundary layer thickness. So the local boundary layer thickness. So you have to first multiply the boundary layer thickness at any given stream wise direct position to find the actual velocity profile. So this is still g of eta. Let me note that out. So that's actually important. Okay, so this is g of eta, not u of y. Okay, let me write that also. Not u of y. We have to do that that non-dimensional, non that redimensionalization that we non-dimensionalization that we had done. We have to redimensionalize it to get u of y. That is an important thing there. Root finding we don't need to do. One important thing is actually in the Bloch's case, in the particular Bloch's case, it is actually interesting to note that we don't need root finding. That is a very beautiful property in Bloch's. We don't need shooting method per se. We don't need shooting. You know why? I'll tell you why. Um, um, I don't know. Maybe is it possible to look at it or not? I think it is possible. So the need for performing the integration more than once is eliminated. So let's read this part of it. So is eliminated on the observation and then okay, okay. So the important thing to note there is, see, so now what we have done, maybe a little bit more time I'll give to Bloch this important observation. In Bloch's case, we actually don't need to shoot because of a beautiful observation in Bloch's equation that it is kind of invariant to a certain transformation. And now let's look at this. So the transformation proposed is that we write uh, um, instead of, so what we write is a function. Um, how do we write this? GHIJKLMNOPQ. Let's say Q is some alpha F and eta is eta. Let's not write eta now. Let's write something else. So eta tilde tilde. What else? What variable should I use? Hmm, let's say rho. Or let me just use x, capital X, which is eta divided by alpha. Okay. So now if I do this, if I write this equation, f, just let's transform this equation to in forms of q and x. So if I do this, so first of all, let's realize what will be the q dash. Q dash will be uh, q dash of so dq by dx will be what? Will be alpha times dq by d. Uh, so df by d eta and then d eta by dx. And now d eta by dx is 1 by alpha. So essentially what you get is df by dx, d eta. Okay. And the same thing will follow for other higher derivatives also. Does that make sense?
Yes, sir.
So
That is.
basically, so what essentially this transformation is doing is that if your q, you can write this part of it, q triple dash is 0. Okay. Now, um, okay. So the point there is, let me think, yes. Mm. So suppose you have guessed f double dash of 0 as, suppose your initial guess was 1. Okay. And with this evolution, your f dash of, or let me say, our guess was on q. Okay. We guessed our guess was on q dash was 0. Q double dash of 0 was 1. Let's say we have taken that. And our final value was what? Was, let's find that value. So suppose it is just, it is this value. Let's suppose I guess it is 1. So we get this value 2.08. Okay, 2.085, let's say. So now, um, yeah. So now, if f dash of infinity infinity has to be 1, can you find me an alpha? What is alpha? Actually, this is a little, I'm going too fast to explain this part, but anyways, so this would be q dash by f dash. Will be q dash by f dash, right? So alpha will be 2.8, 2.08, 5. Let me check what is 1 by 2.085. Somewhere, I don't, wait, some error is there. If equation 2.82 is integrated, a to the power minus 3 by 2. Yeah, see, this is the exact value that you will get. See, I will have to do it more properly. So actually, this is not the equation that we'll get. Got it. This is not the equation that we will get. What equation do we get? That is, did you see what happened there? See, the value we get by any guess value, the correct answer will be this raised to the power minus 1.5. Therefore,
Yes, sir.
and this is a little peculiar. We don't like, why would this be our correct values? Let's say this is our value. Okay, let's see. Then what value do we get? We get exactly 1.00 this thing. So we don't actually need a second guess there. Our first guess is enough. We don't need shooting method. Now let's understand why. See, if we do this part of it, so we realize that q dash dq by dx is df by dt. Dt, not dt, df by deta. Uh, now let's write double derivatives. Then you write, basically you have to write f double dash by alpha. F double dash by alpha. Okay, and then third root will be sorry, third derivative will be this thing, alpha square. Okay, so now if I do this, I write this equation. There I have to write this part as alpha q q. Then this will be what? Will be q double dash uh, by alpha. So this alpha and alpha gets cancelled, and this one will have alpha square q triple dash. Okay. Now I don't remember the derivation also, this part of it, but it's quite simple. Dash of 0. Let me see. Q of 0. Thing. Can you see what is the logic there? Why will this be alpha to the power 3 by 2?
Let me see, sir. I'll try.
Actually, this will be 1 by alpha. Let me, this was, Q was, so this was A by alpha. Okay, and F double dash is, it becomes Q by alpha. F double dash is what? Alpha by Q. Alpha times Q dash. This is okay. And you have alpha square. F dash alpha. Yes. Wait, let me do it properly again. The transformation that we are proposing is Q is alpha F, and eta is alpha by B. This thing. If I do this kind of transformation, then you write alpha times df by deta and deta by dx. Times what? Deta by dx is what? It's actually alpha square. Now, if this is alpha square, this is alpha square q by dx will be and again deta by dx. That is an important thing. Which is what? Theta by dx is alpha cube. I've not done it properly. That is why it seems f double dash, and then this will be alpha to the. Should I do it more again properly? It will be alpha cube. Will be cube alpha to the power 4. If I write everything in q and x, then q is alpha q. F is alpha by q by alpha. And then f double dash is what? Q double dash by alpha cube. Yes, q double dash by alpha cube. And then here you will have yeah, that's fine. So this will be q double dash triple dash by alpha to the power 4, right? So what we see is that this under this transformation, the equation remains see that finally the equation becomes q into q double dash plus 2q triple dash is equals to 1 is equals to 0. Okay, now the important thing is, suppose you have guessed f dash of 0 as some value. Let's say some guess f naught or some value I've guessed. It's a beta, and that results that gives me the q of dash of, let's say, 10 is gamma, right? Mm. But then f dash of 10 has to be 1, right? So now there only it comes. I don't remember exactly how does it come. Like, exactly remember why it's like this. So suppose make sense of this. So alpha is gamma. Give me a second. Suppose A. This is A. Hmm. So now using this part of it, let Q double dash is alpha cube F double dash. So this should be true. Right, see. So now what that makes, yeah, so what they have done is, suppose this Q is 1. Okay, so this is 1. This is 1. Now F double dash of 0 becomes alpha to the power minus 3. Okay, now in that case, what is F dash of 0? Um, F dash of 0 is alpha square uh, Q dash. Wait. I think I kind of get it now. So let's see. So with all this setting, uh, let's say our double dash of 0, our initial guess was 1. Okay. Now, what we write is that this Q dash of 10 comes out to be A. So what essentially are we saying? That uh, now let's use this equation. Okay. That Q dash is alpha square F dash. Okay. And that has come out to be A. Is that okay, Apurv? This part of it. So now you realize that f dash of infinity was 1. So this has to be 1. So this part of it, f dash of, and let me write this also. So this is x is equals to infinity. Okay, and f dash of theta equals to x by, what is it? X by alpha is what? We don't know. X by alpha, it will also be infinity, this thing, because x is infinity. So eta will also be at infinity, and this is we have calculated it as a. Okay. So then we know alpha becomes this f dash of this will becomes 1. So this is alpha square is a. So we know alpha is a to the power minus 2. Okay. A to the power minus 2. And from here we use this third equation, that this is q double dash and this is f double dash. So this becomes that your q dash was, let's say, 1, because this was 1, right? Q dash of 0 was 1. So q double dash of 0 was 1. This thing is also something that we need to find. Uh, this was 1. It should be half. What am I doing? It should be 0.5. Okay, and this thing now becomes f double dash of 0 is uh minus, so alpha to the power minus 3, which is what? A to the power minus 3 by 2. We got this expression here. Acha, let's do one last thing so that we understand this derivation. Suppose this is our some random uh, some random variable. Let's some random value. Let's say beta. Okay, so this is beta. To the So how will this beta go into this entire thing? This this was our initial guess, and we get a. So with this, alpha is known. Now this is beta, right? It's not 1. So this will be beta times alpha minus this. So so if we have done this correctly, uh, this is our f of dash. The correct value should be this, where beta is what? Beta is the initial guess that we have taken, and the value a is what? The value that we have got. So let's check this once on our case. Let's say a weird guess I'll take. So this is, I've taken it as a, let's take it as beta, and this is our beta. Okay. And what is our alpha? Alpha is, so here I will do. So alpha is, or a is, what is it? A is this value. I'm going a little fast, it seems, but let's calculate beta into a to the power minus 1.5. So we should get this nicely, it seems. Okay. So let's guess some weird value. Let's say np dot pi. Okay. We'll get something. Let's plot it and let's see. See, this is what we get. The final value is correct. We get this the final. So why we don't need shooting in this particular case of Bloch's equation? Because it follows this kind of transformation. It has this invariant property which allows us to actually find out. Suppose, see, this should make sense, right? It was a very simple root finding exercise that we were able to do. Uh, we were checking, it was kind of linearly moving if you think about it. Our f of dash of 0, sorry, our f double dash of 0 was kind of linearly moving to 1 as we were increasing our guesses. So we see that there was a linear correlation, or some very what do you say, very deterministic relation between f, our guess, our initial guess, and the final value that we were getting. And so given the value that we wanted, we could actually find the correct value. Did, does this derivation make sense? Because I made a lot of uh, like I was writing a lot of things incorrectly and then revising them. There were a lot of revisions, so maybe this was little unclear, or is it okay?
Yes,
If
sir.
you do,
Quite. I'll rewatch it.
yeah, but if you look at it now everything seems like I've written it correctly. If you follow it now, this one will give you the correct thing. Okay, fine. So I think do we need to do that root finding implementation, or is it okay now?
No, sir. It's okay, sir.
Okay. Now anyway, now let's close this. Achha, one last thing is that we also looked at some eigenvalue problem. It mentions eigenvalue. So where did it mention it? This was something that we were looking at last time. A question was raised about eigenvalue problems. Looked at, found it somewhere here. Tungakutta. It's not here, huh? Shooting method. Or somewhere in shooting method. So the eigenvalue problem is which one? This one. So we can open this up.
Eigenvalue problems arises when is a system of differential equations. Then only it comes into picture.
Well, my understanding is a little different there. Essentially, you have to get something of this sort. When when you have an eigenvalue problem, let's discuss this with ChatGPT. It will kind of let's look at it. Um, so if I'm just writing something, let's see if ChatGPT agrees with me or not. So we are trying to pinpoint how our eigenvalue problems special slash different from IVP or boundary value problem. My understanding is it arises when separation of variable situations there or problems where uh, the solution is a combination of a lot of eigen functions. What what is your understanding on it? Okay, so yeah, this is nice. So these arises when you have a homogeneous boundary value problem, no forcing terms, but the requirement that non-trivial solutions exist only for a certain parameter values. So this kind of stuff, when you have sine and cosine. See, in this case, you will have sine and cosine, right? Y double dash is this is the equation for sinusoidal or cosine functions. This is where I was mentioning even the last time that it has to be of sinusoidal nature. This is more or less related to Fourier functions also. Initial eigenvalue problems are subset of boundary value problems where only special parameter values give non-trivial solutions. So last time I was trying to go through this and see this is where they come. Now maybe this prompt is kind of biased towards my understanding. Let's look at it from my independent point of view. What are eigenvalue problems in differential equation? Great question. Okay. Yes, term. Yeah, this is nice. Vibrating. Okay. Let's see. Eigenvalue problems in differential equations are boundary value problems where solution exists only for special values of a parameter, and the corresponding function forms a useful basis to express general solution. What is the reason all these values as eigenvalues? Hmm. Okay. So it says that it has to be of this format. So eigenvalue problems have to be of this format. This is the general idea. Okay, it has to be so the differential operator on y will be some lambda times the initial so independent function. See, so you see this. Okay, this now makes sense to me. Okay, fine. Uh, okay, so what is it saying? It's kind of saying, suppose we have this kind of equation, dy cube by dt. Say, suppose we kind of have this kind of format, right? Now, when will this be an eigenvalue problem? When your operator can be written as something of this sort. So this, if you can see that this equation can be written as a operator format also, operator form also. So what is the operator form? So this will be written as something like this.
dq plus 5 d square plus minus 2d plus 3.
Yes. So, but how you mentioned the system of equation, I don't understand if it is exactly what you mean. Like if it exactly implies that eigenvalues are when you said that when I eigenvalues, it's an eigenvalue problem when you have a system of equation. You mentioned that, right?
Yes, sir.
But even in our Bloch's case, we have a system of equations.
No, we
Hello.
had only one. We had only one. Yeah, in a way you can say that. I mean, the governing equation was third order. So if you, yeah, we got three equations. That is also right.
Yeah. And I think this is a linear operator also. So L of y is
Yes, it has
L
to be
of
linear differential equation. That is another, I think.
yeah, it's a linear differential
It has to be
operator.
linear.
That's
It
correct.
has to be linear.
Yeah,
So in our Blasius problem, we cannot have eigenvalue because it is non-linear.
yeah, that makes sense. And does it also have to be, does L always have to be first order? Because then any D can be written in L.
It works for second orders also, sir.
Second order. No, see, my logic is, I'll tell you why. I'll tell you why. See why how eigenvalues will pop in. Suppose this is the case. See y double dash plus y is 0, right? In this case, let's write again similar thing. F equals to y and g equals to y dash. Okay. And then I write capital F equals to f and then g, and then my f dash will be, what will my f dash be? F dash will be uh, capital F. So what will it be? It will be 0. This will be 1. This will be 0. And so f dash is g. So this will be 0. This will be 1. And this will be g dash will be 0 of f minus. So wait, this will be minus 1 and this will be 0. So what exactly am I writing? How have I written this? I'm writing f g and g dash. This sorry g and this thing is f. P. So now you tell me in this situation, what are we writing is g dash equals to minus f, and we define, yeah, this is the differential equation, right? So now if I were to write f dash becomes g, so 0 into f and 1 into g, and g dash becomes minus f, so 0 into f, no, minus 1 into f and g 0 into g. Now in this format you will get a matrix
Yes, sir. Matrix is there, square matrix. So we can have a we have the
eigenvalue. The eigenvalues, I guess, let's see what are the eigenvalues of this. So eigenvalues will be trace of this matrix is 0. So we know the eigenvalues will have to be what? They will have to sum up to 0. And their determinant is what? 0. So determinant of A is what? 1. Which means that the two eigenvalues will multiply to have values of 1. So the eigenvalues will be lambda 1 comma lambda 2 is plus minus iota. You see that, right?
yes,
It
sir.
will be no, no. Wait. Plus 1 and minus 1. Huh? What are eigenvalues here? So lambda should be minus 1 or 1.
Plus minus I will be the eigenvalue. Plus minus iota.
Determinant plus minus 1, right? Plus minus iota, right? What were you saying? Didn't catch. What were you
One
saying?
minute, 1 minute, sir, I'm solving.
That is why we'll get sin x and cosine x in this case.
Here's a plus minus iota.
Plus minus, right? Because this
Yes,
iota square is minus 1 and then minus 1 is plus 1. This has to be, this is, and then iota and minus iota, you see that it becomes cosine x and sin x, right?
yes, sir.
Because e to the, so basically what you're getting is e to the power iota and e to the power minus iota. So see, basically what you're getting is e to the power iota, and then you will also get a component of e to the power minus iota, and you will have a constant of proportionalities there, a1, and let's say not a1, let's say a a1 and then a2. So your solution should have something of this sort, right? Eigenvalues. Now we know that. You're saying something.
No, sir, go on.
uh, yeah, there will be some x also, I didn't write that. Now we know for the matter, for that matter is
X will
that,
be pi by 2. Yeah.
yeah, pi by 2, yes, you have to write it as pi by 2. 2, right? Write it this way only, no? Let me think. Yeah, e to the power iota pi by 2. Yes. And minus pi by 2. Yes.
Maybe it should be only I only. Pi by 2 should not be there. I mean, the
It will, it
answers
will
should
be
be of
there.
the form e power I lambda
So we are
x,
writing
right?
it in the polar coordinate. We are writing when we write this, we're writing it in the polar coordinates. So any complex variable will have to be written it like this, right? E to the power iota theta. That's why iota will be there. No? Let me ask ChatGPT only. Uh, give eigenvalues, eigenvalues of this guy will do it fast. 0, 1, then -1, 0. Meanwhile, I can't be always.
I think we
Okay.
also need to find the eigenvectors.
Hmm? Yeah, we need to find eigenvectors. That's true. Yeah. So how would so we are kind of digressing. Maybe this is a very short problem. So, anyways, he has kind of answered this. So, not every differential equation is a eigenvalue problem because boundary conditions are important. See, he says, so I was not, this is not right. Not every equation can be posed as a eigenvalue problem because, and also L does not have to be a first order problem. It is not restricted to first order. It can be a second order also, or
Only
even
thing is,
higher order.
yeah,
Hmm.
it has to be linear. That is the only thing, I think.
Yeah, it has to be linear. So did you read about this from any book or somewhere? You know a source?
Yes, one professor from Hong Kong. He has his video lectures. I can share the link on in the chat.
Yeah, just do that. Maybe we'll look at that as well. But anyways, and so you're aware about this fact that when these two boundary conditions have to be imposed, only certain lambda can satisfy this eigenvalue. Maybe I'll try to. My problem. Yeah, you've shared the link. Let's look at the link. Link.
It's a vibration problem. I
Yeah,
mean,
that's
uh, second degree of freedom vibration problem. Two oscillators are there.
okay. Okay, so he writes it this way. Great. And now there is a boundary, like there is a matrix there. Oh, the equation you have shared is not that I can. So I should look about the normal modes, huh? This one, MRV square is this thing.
V is the eigenvector.
Oh, I get it. Yes, yes. Yeah, so okay, fine. So this is fine. Okay, I get it. Hmm, the only thing, so maybe I'll open that book. Let's see. Okay, this I understood what you were saying. This is the chapter. Maybe there is a reference book that we can explore. Let me open this up. Boys Deep Emma. Thanks for this video. I now understand it. I have kind of now I kind of see where this all is coming from. Because essentially we don't I've not read a proper set of this like proper except on eigenvalue problem. I've heard it like in passing.
So,
Anyways, you said something, huh?
no sense.
So this is the like the textbook for differential equations. Um,
I think in crazy is it's there or not. I have to see.
which one?
I think in crazy also eigenvalue problem is discussed. But
Yeah, maybe if you can just find it, if you can just look it up there, and if you have the book with you, fine. Yes. Uh, See, eigenvalue has to be of this sort only that it has to have a eigenvalue kind of format that a lambda, so ax equals to lambda x kind of stuff. Hmm. But then in sort of differential equations, how are boundary equations coming in? How are boundary conditions imposing that fact? This is where I'm kind of but essentially we understand that eigenvalue problems are a subset of boundary value problem. They are not a different problem of their like they are not a different category of their own. At least that is clear.
yes, yes. No, that person last week he was that statement was wrong. That there are three kinds of problems: initial value problem, boundary value problem. Then he said there is eigenvalue problem. Type is different. That statement is not correct.
Yeah. So even I understood eigenvalue problems from that lens only that you have to have certain boundary conditions that you have to satisfy and only certain eigen functions are there which can satisfy those values. Yeah, that's okay. So they use this differential operator. Differential operator is a very like it's a very standard basic thing. So even you see here, you get e to the power r1 and r2, where we are solving this characteristic equation, right? Just like how in eigenvalue problems also we have a characteristic equation. Okay, so maybe now if we look at it, if these a, b, and c, okay, so now I can write this as L of y is minus c of y. Okay, okay. If my but then how are boundary conditions coming in? That is where I want to see why boundary conditions are making it an eigenvalue problem. Because for eigenvalues, you just need a matrix format. You don't need eigenfunctions. Like there are no eigenfunctions as such. We have only eigenvalues and eigenvectors, right?
Yes, sir. But if we get the solution, say y equal to in the form of eigenvalues and eigenvectors, so like the eigenvalues and eigenvector will already be a function of the independent variable, right?
Hmm. But not able to
I
properly
mean,
understand that.
I mean, I mean, the answers in the video, if you watch it, it is of the
This
form
one,
of the
this video, huh? This
yes,
video
sir.
only, huh?
Yes, sir. In that one,
Okay.
the ansatz is of the form like eigenvector multiplied by e power lambda t, where lambda is the uh, eigenvalue. So once we get the solution, so what is the problem in implementing the this thing boundary problem?
So
The solution
where is it? Which where
maybe you can watch the next video, lecture number 47.
okay. Here.
Yes, sir.
Okay, so what does he say? That if you have this kind of format,
I mean the
then
ansatz
V is the
is
eigen function, huh? R is the eigen.
V is the eigenvector. We have to find the eigenvector. See, try xt equal to v e power rt. So v is the eigenvector. We can find it. R is the eigenvalue. So we'll have the xt as form. We'll get xt.
Got it.
So t is already there in the RHS. So we can use have the easily put the boundary condition. I mean t for some value of t there will be some boundary condition. or initial
Found
value.
using the boundary condition. You find your eigenvalues using the boundary conditions. Oh, okay, okay, I understood.
Eigenvalues is not dependent on the boundary condition. It is like in this vibration problem, the stiffness he is writing down the. I mean, um, yeah, eigenvalues um, is a function of the stiffness of the springs, so it does not depend on the boundary value. R1,
Okay, so eigenvalues, okay, okay, that makes sense, makes sense. It's not the eigenvalues that are dependent, their contributions are dependent on the boundary value, boundary condition, right?
somewhat,
At least
somewhat, like, yeah.
yes. Okay, okay. So the eigenvalues won't depend themselves on the boundary conditions.
Yes, yes,
But even in this set of in this equation, my only reservation is like I want to kind of look at in from a generalized lens. What I'm trying to see in this case, I am able to understand how he has written it very nicely. But this is
yes.
still a second order operator, you see,
Hmm.
and
Yes,
in a general sense, we can have any sort of differential operator. In that case, what is the like when will it be an eigenvalue? Suppose why this is not an eigenvalue. I'm trying to understand this. Why this is not an eigenvalue, or if it is, then what is the eigenvalue or what is the eigenvector there? Is this so?
I can we can have eigenvalue here if eigenvalue problem here if we can convert this third order differential equation into lower order differential equations. I think then we will be able to formulate eigenvalue problem for this one also. Just
Only with that
yes,
thought process only I wrote this fact. That is, does it always have to be a first order? Because if you keep reducing it, then you will increase the dimensionality of your dependent vectors. But he says that no, it does not have to be it does not have to be a first order. It can be a second order, even higher order. It says that.
sorry sir,
You
can
understand?
you
So
repeat
just like how
once?
you mentioned, right? Just like how you mentioned that if we reduce the dimension
Order.
this order of the equation to
Yes sir.
smaller thing and then
Yes sir.
write it, then this can be an eigenvalue. You said that, right?
Yes
I
sir.
I
Yes
was
sir.
I was thinking on the same lines. But if you
Hmm.
keep reducing it, the lowest you can go is to first order only.
Yes sir.
Then
First order.
but then he says that eigenvalues problems don't have to be first order. He
Don't
says
have to be
that.
first order. I mean, we are converting that third order, right? So
Okay. So
we
but
are able to
essentially you're saying that
third order.
when once okay, so once reduced to first order, then it has to have that format.
Even this vibration problem was second order only. Still, it was we are able to get the solution.
Okay, but then where does he reduce it to first order? Like where does he do this? How is A? What is A? Where is A coming from? See, A is
Is
coming. See, A in this case, A is coming from. He's trying a solution. He's forcing a solution there. A does. A is
yes
not
sir.
coming from. And
Yes
this is
sir.
again a second order thing. It is not a first order thing.
Hmm.
But
He is
again,
just
it's
taking the answers as
small.
B e power RT that way.
Hmm.
He is taken from this from the governing equation maybe. No, try
Hmm.
extreme V e power RT then MR square.
Because see, because essentially we know that see, essentially this equation which he has written down is the same equation which I have written down now, right? It's just that his like in my case, A is one,
Yes, sir. One.
right?
Yes, sir.
And for this particular equation, we know that this will arrive as a exponential function,
Hmm.
right? If I write r here, I know that it is either e to the power under root r or under root minus under root r, right? It is using the property of exponential functions.
Hmm.
My only concern is on a general level, what is the eigenvalue? Maybe I'll look it up. Maybe later we'll look into that. That is something, yeah, not very well established, it seems. You were mentioning some book. You sure about? Maybe I'll explore if this book mentions something. This is a textbook for differential equation, Boyce and D. Prima. Yeah, you're aware of this book?
No, sir. I'm seeing it for the
No?
first time.
Okay. Oh, it mentions eigenvalues. Let's look at it.
Again, here, yeah. Yeah. Yeah, that is a no. It is not in relation with differential equation. It is just from linear algebra point of view. I think you should be going to
Somewhere
the
they will introduce differential equations, right? This is a book on differential equations. Let's see.
okay.
Is it- No, I understand what you're saying.
Yes,
At
I got
that page,
that.
it was
Hmm.
hmm, actually nice. He actually asked a good question because eigen be used like I have read about eigenvalues in a passing sense, not
No, he
like
was taking eigenvalue to partial differential equation also.
yeah, that that part again.
Translation of partial differential equation.
Yeah, maybe yeah, that was a good question because sometimes we are using the same nomenclature everywhere, so it can be confusing. That's true. So yeah, that confusion can obviously arise. Naturally, it will naturally arise. That's correct. Hmm. Complex eigenvalues. But see here, he is using X dash. So like just like how I was saying, first order. The first order, but not using a general operator, at least here. Again, even we, or at least me, I'm not also looking at it very, what do you say, strictly. I'm just looking at it very quickly so that we just move ahead. We're not very much interested in what's going on behind. Like he was right. Even in that case, we will get some eigenvalues. But for sure, those characteristic lines are not associated with any eigenvalues or anything.
Characteristic lines. Actually, he was taking that from this thing. Mm, Potential supersonic subsonic potential flow equation 1 minus Mach number square dou square by 5 by dou x square he was
But
taking.
there we don't use the word eigenvalues. I don't think eigenvalues are used in that context. Not
I
sure.
can share that video say if you want. Um,
Yeah, maybe
uh,
we can look it up. Maybe we can give 5 minutes to
1 minute,
that.
I will show.
If that is the case, if so, they use eigenvalue in that context.
Yes, in for classification of partial differential equation.
Okay. No, but that is different. Classification of PD is different, and characteristic lines are different.
I think he mixed up.
Okay. Eigenvalue problems in PDE. Just look at this one. How we have to do separation of variable here. The unknown variable is written in two separate. Generally, eigenvalues will come in this sort of format also. Ah, interesting. So a linear operator and then there is an eigenvalue. Nice. But see here also it has the no, it's not the first derivative, it's a second derivative only. Okay, okay. You shared anything? Not yet. It's okay. Shared something. Good. Let's look it up. So mostly you rely on YouTube for your learning, or you explore anything else?
YouTube is reliable, sir. Also there,
Good,
but
good. I was just asking like what is the okay.
I
I was
think
asking
I think I shared the wrong video. I think it should be the next one.
next one. Okay. See, even here, there is a separation of variable must be going on. I'm pretty sure. Let's see. He must have written this down. Zeta as x minus ct.
Now he is transforming.
Yeah. So once you do that, see, yes, at this point, phi is written as a function of eta and zeta. There's separation of variable going on. Um, but where is eigenvalue as such?
1 minute,
Because
1 minute.
eigenvalues, I don't see eigenvalues. I don't mention eigenvalues here.
Just 1 minute, so let me check
Ah,
once.
I'll wait. Actually, these videos are classic videos, textbook
This
material.
video will go, if you fast forward,
To
so,
which timestamp?
uh, so fast forward to 42 minutes.
42 minutes. Yes. Okay. But see again here, it's not eigen. Acha, this is nature of characteristics. Okay. But yeah, like at this point, basically we are saying if they are if eigenvalues are real, then you have what do you say? Parameter this hyperbolic equations if they are uh, non-existent. No, what is it? If any lambda is zero, then parabolic. If one is zero and all lambdas are of same sign, elliptic. Okay, this part of it I'm not sure. Depends on eigenvalues of A. But eigenvalues of A,
You have to expand the PD. I mean, the summations are there, right? That you will have to
yes.
expand. Then you will get A11, yes, A12, this way. So these
Okay.
using A11, A12, you will get this square matrix, and then you find the eigenvalues. And he has given an example for this um, potential flow equation.
Potential flow equation.
Yes, sir. That one minus.
Where?
Go back.
Okay.
And this is potential flow.
This so basically this is the example, huh?
Yes, sir, yes, sir.
Okay, okay. And in this is the characteristic line dependent on the eigenvalue?
It will depend, sir. And
See, no,
um,
no, it does not depend. See, it depends on the Mach number.
Mark number, yes, yes, sir. That is more accurate. Correct.
And Mach
I
number
say
will
also.
decide whether your lambda is zero or positive or whatever. This part I am
Yeah.
not sure. This part I am not.
Yes, sir, yes, sir. You are right. It will depend on Mach number only. Then only whether it is parabolic, elliptic, or hyperbolic.
But they are not physically related to any slope of characteristic line at least. Even
No,
in
no,
this case, right?
no.
Okay, okay. So at least okay. But I understand what because this A is kind of representing the nature, like what PD it will be, whether it will be elliptic, parabolic, or hyperbolic.
Yes, sir.
And it turns out if
I tried
the
this thing
lambda is
with other PDs, but I was not able to do it. And this one is okay. Like
what you
if you
you
try
were not
finding
able to do it. Hmm.
like using the same technique for other governing PDs, then it was not working that way easily. This one is
Okay.
quite simple. 1 minus m square dou square 5 by dou x square. It's easy to see.
Okay. Okay. Nice. Good. Okay. Got it. Hmm. Okay, got it. Yeah, it's a little complex. It is not that easy. But do you require that much of? I didn't know that you required this much of details in your other courses. At least this is definitely not needed in this course. I'm pretty sure. But good.
Yes.
So you're doing advanced courses. Good. Yeah, fine. Nothing to close there, right? Everything we've discussed it. Yeah, nothing to. I don't have any remarks to make anymore. Yeah, it's a little more out of something that I prepared for. Yeah. Okay, fine. What we'll do for the next 1 hour is, or more likely 45 minutes, is look into this numerical linear algebra. Okay. And it was you only, Apur, right, who asked about I think TDMA and LQ decomposition a little bit on that, right? One day.
Yes. Yes.
Okay. So I was looking into what to so after our finite approximation method discussion, I was looking something into this part, numerical linear algebra, and I found that something that we have not and generally is not explored is singular value decomposition. Okay, and maybe we can look into that a little bit. And a small motivation I had discussed, I'm not sure if you were there that day, where we had looked into image compression using SVD. Were you there?
I watched the videos on YouTube. So, but I have a
Okay.
question. Like, what is the use of SVD um, in our mechanical or aerospace? Do we have any use?
A lot of I think it's very important because it is a numerical technique after
Yes,
all.
it's a good thing that yeah, we can write a matrix in form of like multiplication of three different matrices. That also rectangular matrix. That is useful thing. But is there any practical use?
Otherwise, otherwise you're asking, right? So essentially, what I realize is that it is a essentially a data reduction technique. That
Hmm.
is the so you can have a lot very fine data. Suppose you have a image, right? If you have an image, like for the example of let's go to that image example. Image can have a lot of fine features. It can have coarse features also. And mathematically, you can represent. So see, this one has a lot of boundaries, like very sharp boundaries. It will have. There will be. You realize that, right? This can have very fine features. But suppose in your model, and this is essentially image is a data. So you can have fine details also in your data. But suppose you don't need that much detail, especially in CFD or stuff. If you want to reduce the order of your model, if you want to reduce the amount of data it is storing or it is operating on, then you can use SVD. Then the next thing is principal component analysis. So maybe something on that also I have principal component analysis.
I've
And
heard of I've heard of this thing.
you've heard of this?
Yes, actually, I'm
Yeah.
also in one machine learning course, so it is there.
Yeah. So essentially, it goes towards that direction only that you do this machine learning and stuff, trying to see if there is something on model reduction. So while preparing this material, let me see if I have that there or not. Untitled, do I have it there? Essentially, what I was looking at was reduced order modeling. That is an important aspect in, especially in our mechanical engineering and um, kind of setting. Uh, what I realized is that any transient uh, evolution could be represented by much smaller, what do you say, much smaller sizes. If so, suppose what I had done was I was exploring this with Gemini, and I was looking at the problem that kind of something like this problem, and I was trying to solve a differential equation. This was a transient differential equation this time, and it did not have this unsteady heat generation term. It was this was a unsteady heat transfer equation 1D only, and we used finite difference. So let's say 100 nodes for this. solving this PDE. Now, using SVD, what we realize, what Gemini showed to me, using SVD, only 3 points were enough to represent or at least model this what do you say? Model this solution or model this heat transfer problem. Only 3 nodes were important, and we could actually go ahead and use those SVD decomposition to get to solve, like, to create a low order model. So, and the accuracy was the same. Accuracy was slightly lower. Slightly lower means it was in order of magnitude lower than, say, accuracy was 90%. So the difference was only, like, suppose with 100 nodes, you're getting accuracy of 90%. So with the reduced order model, let's say 3 or 4 nodes, what you were getting was, um, let's say 89%. So with a very small drop in accuracy, you would get the same, you would get the same very low, very high data reduction. So I have that code with me, but I've not gone through it. Maybe I can show that to you, and maybe then we can look at it later, because I've not prepared for that part. Let me see. I've so let me see. Kind of had prepared that thing, but I'm not ready with it. Okay, not this one. This one. Maybe this one only. Let's see. We can copy this up. What's going on with this?
I mean, the only application for SPD is for image only, nothing else.
No, 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 no. How did you come to that conclusion?
I'm asking because I have not come across anything else.
Yeah, that is
I got exposed to
I mean,
SPD because I was watching linear algebra lectures from Gilbert's time. So he he, he was saying this only. Image compression is useful.
no, no, it's very useful. It is very useful. I'll show it to you. I'll show it to you. Wait, I'll show it to you. It's very useful. It is actually a very unfortunate thing that it is not discussed. And the reason behind it, actually, that was something I was exploring. See, let's read this part of it. Actually, when I was preparing our material for this, it was actually the first thing that I was interested in, that why essentially it's not explored properly. See, let's read this part of it. See, it is curious. It's something that it's an important part. So let's read through it. So decomposition or canonical representation lies at the heart of matrix theory. The ability to reduce a complex matrix into smaller constituent parts that reveal its structure and properties form the foundation of numerical linear algebra. Among the many matrix factorization, the singular value decomposition stands out for its unique position at the intersection of universality, geometry, and computational stability. Originating from the pursuit of eigenvalues, it goes one step further by providing a general framework that applies to all matrices. It is curious then why such a profound technique has not found a central place in most undergraduate or even graduate courses on numerical method. Now look at it. The likely reason is curricular necessity. The classical decompositions like LU decomposition or QR or eigenvalue decompositions align more directly with canonical problems like linear systems, least square, or stability, and thus demand priority in syllabus before advancing to a more general frameworks. So the reason that this is not explored in any course or anything is that it is too complex for our introductory course or anything. It requires you to spend some time on it to actually
Yes, sir.
realize its benefits. So I'll show it to you. This is something that I wanted to cover or emphasize on why SVDs are indeed quite important. Okay. So let me just before that, what is this command A, command X? There, wait. So we were where were we? Look, this one, no? I'll show it to you. Wait, what is going wrong? Acha, this happened. Okay. So I was thinking what stopped? Server stopped. I'll show it to you. The first application, just to point out, model reduction is a very important technique, by the way. And I think it is SVD which uses model reduction. Like model reduction is essentially using SVD, model order reduction. It's a very important aspect of like, but it comes as a, it's a advanced topic. Especially it is used in control systems, even in numerical simulations, and what else? And it is based on this orthogonal decomposition. Maybe it will have singular value decomposition also somewhere. See, singular value decomposition is an important aspect of model order reduction. Can't emphasize too much on that. I'll show it to you. Essentially, it is, as you said, a model reduction technique. Sorry, data reduction technique, like how you said, image reduction. That is what primary objective of it is. But I'll show something to you today, which will highlight the importance of SVD over other decompositions also. So, for example, SVD is very important when your matrix is very of a very peculiar nature. That happens a lot. Suppose you have a very stiff system, then your SVD is your only go-to method. You can't rely on anything else. We'll discuss that part. Let me run this code for you. This code which Gemini had generated. So see, what are we trying to solve there? It's a 1D unsteady heat conduction equation, and this is the initial what do you say? Uh, see, you can read the legends here. You're there, right? Pur?
Yes, I'm here.
You're here, right? This was the initial temperature distribution of a 1D heat conduction problem. Okay, a
Hmm.
1D bar. This was the initial heat conduction temperature distribution in a bar. Now, using our finite difference method, we evolved over time. Okay, and you see, this is the what is it? FOM is what? FOM must be FOM is what? Don't know FOM is what. Let me check. What is FOM here? Full order. Yeah, full order. So now in a full order model, you are full when you're solving it with the finite difference model. This is the predictions it does over different times. Now you look at the reduced order model. The reduced order model is doing the same thing. No, you can't, there is no apparent error, at least there. Okay, look at the error. It's so small. And this is the dominant modes using SVD. So my only submission to you is that look at this curve, and essentially we have stopped at how many we have truncated at r equals to 5. Let me truncate it at a lower value. Let me truncate. Basically what I'm trying to do is that in this problem there will be a large number of modes. Okay, so there are around 100 modes. Okay, the SVD is first of all telling you that not even let's say 10 or 20 modes are important, you look at how uh, the importance is decreasing. So this magnitude is kind of showing the importance of different modes in your problem. Roughly there are 100 modes, but look at the drop in the magnitude. The first node is 10 to the power 2 or something lower than like 10 to the power 1 or something. The next five nodes are going so low in their magnitude that it's 10 to the power minus 2. Now let me show. Here you don't appreciate it because you're seeing sharp overlap, right? You don't realize that there is actually something going on. Let me reduce this order so that we can actually, uh, what do you say, appreciate what is going on there. Okay, so let's reduce R to 3, where R is the number of dominant nodes that we will keep. Okay, so now we have kept, and now you see the reduced order model is kind of misbehaving. See, it is kind of not accurate enough. But if we go to R equals to 5, it is very accurate. So even let's look at lower orders. Where is R? Where is R? Where is R? Where is R? It's here. So now I have decreased it even further. And now you see that there is no, like, the errors are quite large here. Okay, over time. They are not small. But now let's increase it to the dominant modes that we will keep, or the amount of uh, compressing of the data that we are doing. We are kind of compressing it a little less, not compressing it to the lowest values, but little less. So keeping the most, like, how many dominants we have kept? We have kept R equals to 5. So first 5 nodes we have kept, and you see the errors are very small in this case. So in the order of 10 to the power minus 3. Let's go even further down. Okay, let's take a even higher number of dominant modes. It will be exactly matching. See, look at the error. The error is 0 at 0, but it goes a little bit into 10 to the power minus, like 6 into 10 to the power minus 3 at higher number of um, times. Okay, let me increase this and show it to you what is going on there. L is fine. T, let me increase T a little bit to 20, and then let's see what goes on there with. So this is a reduced order modeling business going on there. So there are errors. Definitely there will be some errors. You will have to take into account larger number of nodes if you want 100% accuracy. But you look at it, this entire data or discretization that you have done. This is C. You have discretized it over 100 discretizations you have done in your high fidelity model order equation. But with your model order reductions, you're only using 5 nodes. Okay, 5 nodes, and you're getting the exact matching there without any like large drop in accuracy. Remember how the accuracy drops with if you drop this, if you drop this, um, uh, let's say if I drop it to say 20 or 5%, let's say, you see how bad the see with 5 distributions, like in your full order with 5 nodes on finite difference method, you look how your approximation is so bad. Literally, it is very bad, right?
Yes.
If you are finite approximation, if in your finite difference approximation, if you reduce it to 5 nodes, the approximation is very bad. But look, with use of SVD, it is so accurate. That is the strength of SVD there. Okay, so
Yes. Yes.
so I spent too much. I elaborate, like I give too much stress on this fact.
So,
So
now I can I appreciate the use. It's
okay,
very useful
now
then.
yeah, it is quite good. Anyways, so this thing we'll try to code this out at some point of time. I'm not ready to code it out myself. I'll have to
Hmm.
go through this code properly and look at it what is going on there. But anyways, one thing which I can actually discuss today is the very outright weakness of LU decomposition when it comes to some peculiar, like some special, what do you say, some special matrices. Okay, so it's called a condition number. We'll discuss it later. So let me properly go through this part. I
That
have
is also
prepared.
like ratio of eigenvalues, right? If
Yes,
I'm
it's an issue of eigenvalues. Yes, you're right. And also SVD, if you think about it, see what kind of decompositions are you aware of matrix decomposition up till now?
LU, LDO, then eigenvalue decomposition, then SPD also. So not
Yes. Now, if you keep SVD away and only eigenvalue is kind of giving you information about what that matrix is doing, right? Only SVD gives you some geometrical intuition of what SVD is doing. Even eigenvalues don't give you any geometrical like information unless you give that analogy which I discussed last time. That in that direction, in the eigenvector direction, the matrices are only scaling, and eigenvalues are those scalings and nothing else. You remember that, right?
yes, sir. Stretching and
LU decom- LU decomposition. Does LU decomposition tell you anything?
no, sir. I don't think so.
Actually, LU decomposition emerged from. Let me open that part. Yes. So let's discuss this thing. Okay. Yeah. See, LU decomposition actually, there are categories. We can actually categorize our decomposition from their emergence kind of fact. Like how did they emerge? Okay. If you look at it, there are five categories. There are basically six categories where which from which factorizations or decompositions emerge. One is based on Gaussian elimination. Okay, and which is where LU decomposition finds its roots. It's basically finding root of system of equation, finding a solution to a system of equation. Okay, it's an algorithm. It does not tell you anything of what is that matrix doing or anything. There is no intuition, and that is why sometimes our numerical methods fail. You know that, right? There are explicit methods, there are implicit methods. We in a numerical, whenever you have a problem, there are convergence issues, right? Whenever you solve for a
Stability,
numeric, there is
stability,
non-intuitiveness in numeric. Huh?
stability issues, sir. Right?
Yeah, stability issues. There are convergence issues, and why are they coming? Because you don't have that intuition about your matrix. You don't understand that this matrix is will result in non-convergence. That one-to-one correlation is not there, right? Whenever you're trying to suppose you have a what do you say, some metric, some numerical method, you're implementing, some problem you have. Some people see that the scheme that you have used. A lot of time we say that let's use upwind scheme, second order schemes or first order schemes. This scheme will become unstable. There are you know, you remember that, right? You must have heard of it at least. Part of the reason is that we don't understand those matrices that we are creating. We're just hoping that they work. Essentially, that is what it is. And in some sense, Gaussian elimination is also about that. It is a, no doubt, it was a seminal work. It was a remarkable work of its time. It did solve a very big problem. But we have to realize that there is no intuition there. There are other decompositions also, which are based on orthogonality. Maybe we'll talk about it. And uh, then there are eigenvalues decomposition. So eigenvalue decomposition is also something that emerge. And this is where singular value decomposition finds its roots. So there are different categories. We won't be able to appreciate every category, but at least we know that there is a Gaussian elimination umbrella, and there is a eigenvalue umbrella, and there is a orthogonality umbrella also. Maybe we'll look at into that also a little bit. But let's go back to this notebook. let me show you how a LU decomposition looks like. Okay, so just for the sake of um just for the sake of completeness, I kind of plotted this thing just to visualize what LU decomposition looks like. What is it? Matplot.p. Yeah. So suppose I have taken a random matrix of size 32 by 32. Okay, this is what I have done. What I've done is in this plot, I'm just showing you what are the different values A contains. Now, what LU decomposition does is it has certain row operations, right? That row operations are kind of stored in P. P is a permutation matrix. It stores like that row operation that you swap two rows or something like that, right? You swap two rows. That is what is stored in permutation matrix. Uh, the purple color is 0 and the yellow color is 1. So basically you're swapping two. That is what is being stored in P. And then L will have your lower triangular matrix, and then U will have your upper triangular data, and then P times L times U will give you the original matrix. So maybe we can also plot that quickly, and then P times L times U, just to see, just to verify this. See, so they are kind of exactly same. You can even play around with them. So they are, this one even looks same, but it is not. Okay, so we have to multiply P times L times U. So this is as much as visualization or intuition you can get from PLU decomposition. Okay, and they also fail at some point. So that let's look at that also. Okay. Hmm. Yeah, where was it? Hill conditioning. Yes. Oh, I have gone to we are out of time. We are 30 minutes away. Like too much. We have gone too much. Oh, I didn't realize this. Sorry, I have to stop. This is too much. Apur, we have to stop. I'm 30 minutes
Yes,
into
sir.
the. Yeah, we'll do it next time.
Okay, sir.
Okay. Yeah.
Yes, sir.
Bye.
Bye, sir. Bye. Thanks.